Thank you for the introduction. My name is Simon Moll, and this is on joint work with Sebastian Hack on partial control for linearization. So we are in the context of SIMD computing. There's a lot of parallel compute potential locked in today's SIMD hardware. Basically, every major CPU manufacturer has SIMD support in their hardware. Let it be ARM, IBM, Intel, NEC, RISC-V, so loads of them. So in a vector instruction, we basically have one instruction that processes multiple elements that are stored in vectors in a single go, in a single instruction, like a map in a functional language. However, it is tedious to program these SIMD instructions directly, so you can use intrinsics or assembly, but that is unproductive. So instead, what we use is implicit SIMD programming through data parallel languages or parallel loops. And say I have this code snippet here on the left, and I want to vectorize this in the that variable I. So what I can use is, I can use a data parallel language, as I was saying, and I would correspond to the thread ID. And examples of these languages are OpenCL or SPIR-V. And for example, OpenCL would write something like I is the local ID, so the work item ID. Or I can also use something like ISPC. And here I would specify, write down basically a parallel loop, and I would be here the iteration variable. I could also use automatic loop vectorizers, for example, shown here for OpenMP4 pragmas in C. So I would write down a regular loop, I would put a pragma on it, indicating that this loop is parallel, just like the one above. And then there's full function vectorization, which can also be triggered through OpenMP4 pragmas, but also directly with other tools. So all these give me a means of specifying that I want to have this code vectorized in a variable I. But no matter which tool you use, you always run into the problem of control divergence. And here's this code again. And we can see, okay, this is basically a short circuit evaluation of an AND conditional. And so if we look at the control flow graph this corresponds to, we have the entry block A, there's a branch, and this branch here depends on the first condition. If it's true, we keep going on with the evaluation of the condition. We go to this block B here, and we branch depending on this value param. And if both are true, we go to C, which is basically the body of the statement. Otherwise, we're going to skip to block D. Now, what happens in the context of vectorization of data parallel languages is that the first condition, since it depends on the loop iteration, will be varying, meaning that if I execute this code with multiple parallel threads, some of them will go left, some of them will go right. This is called a varying branch. However, the second part here will break down into a uniform branch. Uniform meaning that all threads that reach this point will either go left or right. They can't go both ways. So, but what's the problem here? Well, the problem is we do not have a vector branch instruction. We do not have a SIMD branch instruction. So we usually resort to something called if conversion. That's been around for a while. For example, earlier work is by Ferrante in '87, and there's also work by Kernberg and Hack in 2011. So what you do is you basically remove those branches and end up with a linear sequence of blocks. Now you will execute all of these blocks, but you cannot, not all of these instructions can actually have an effect, because you're doing now executing more instructions than you're supposed to do. So what do? Well, you add predicates. So this first condition here will define a predicate bvar, which is like a Boolean variable. Same goes for param, which will just be now this Boolean variable puni. And if I want to find out who should actually execute this block C here, I'm going to add this predicate to this operation. So only if PC is true, I will actually execute this. Now, what is the problem here? I mean, this seems to be a solved problem, right? So, say I have two threads, and I want to execute them in one go using SIMD instructions. So, and let's say the first thread executes, evaluates the false here, and goes from A straight to D, and the other evaluates the first part to true and the second to false, so it will go to B and then skip to D. And this is the code we've seen before, right? Now, if we look what happens on the if converted graph, we will see that, okay, both start out at A, both continue to B. However, the first thread actually doesn't want to perform any operation on block B because it's not supposed to be here anyway. So this value PC for the first thread will be false, meaning that we will execute B, but only with half of the possible utilization of the vector units we could have. So we only perform one operation where we could perform two. Then block C will be in the way of execution because it's linearized, but none of the traces, none of the threads actually want to execute C. So PC will be false for both of them, meaning we have a utilization of 0 out of the maximum we could get. And then the reconverted D where both want to add up. So what happens is basically if param is false here, under that condition, the utilization at C will always be 0, which is bad. We don't perform any productive work. So what is a possible solution? Well, let's go back to the original graph. So ideally, we would preserve the branch at B, because then, if you look at our threads again, we'll see that A goes to D. First thread goes straight from A to D. Second thread goes from A over B to D. This is now still possible in this graph. It's not necessary to execute C every time, because we will only execute C if param invalidates to true. And that means that what I just said, if param is false, then C will be skipped. And the utilization at C, given that A has a probability of 50%, will be 50% in average. So we increased utilization under the condition. And that's called partial if conversion. In this work, we present a partial if conversion algorithm that works for arbitrary unstructured control flow graph as long as they're reducible. Now, there's been a lot of work in that area. And say we have a code like this here, which is a binary tree element search. And you can actually get a 26% speed up over scale execution in this code with our approach. Now, if you see the approaches that are state-of-the-art currently, you could have ISPC, which is only for ASTs, really, so you can't do it for arbitrary control flow graphs, so that is ruled out. You have the approach by Intel and OpenCL, which requires some structure in the control flow graph, and if you do not have that structure, well, then you will get overly pessimistic results. Then there's also an approach by Kernbeck in 2015 implemented in the whole function vectorizer, but that is prone to irreducible control artifacts, and it's a very complicated algorithm. Then you would ask, what is implemented in today's compilers? Well, that would be complete if conversion in case of Clang LVM. And actually, at this conference, in PLDI 2015, Ren et al. Presented an approach where basically, and this is a quote from the paper, it was necessary to perform selective manual vectorization for branches because ICC couldn't handle them. It wouldn't vectorize otherwise. And there's also earlier work, again by Ferrante and Mace in '85, which is a program dependence graph-based approach. So that implies that you first have to construct a program dependence graph, and then you get this algorithm which is slow and also doesn't give you any guarantees. To summarize, existing techniques are either very restricted, meaning they cannot handle arbitrary control, or at least not arbitrary diversion control, or they're too complicated in terms of runtime or in terms of the implementation. So what do we contribute? So partial linearization, again, is an if conversion algorithm for unstructured control flow graphs. It holds out with state-of-the-art on structured CFGs, like tools like ISPC or Intel's OpenCL driver, that implement partial if conversion. So we don't lose anything here. It is fast. It has linear running time in the number of basic blocks. It just scans through the CFG. It is simple. It's really just a couple of lines of code, and I'll show you a walkthrough later. And it's very general because it only requires reducible control, and otherwise you can have arbitrary diversion control in your graph. And we also proved a couple of properties that we'll detail later. And we used those properties to simplify existing techniques for automatic vectorization. So these techniques are re-implemented, exploiting the properties of our algorithm, so these techniques in turn become much simpler. And we've done this for the transformation of divergent loops into uniform loops in a standalone transformation pass. And we also present an approach that inserts all false predicate tests. That's also known as BOSC. That's becoming much simpler. And we show this later as well. So let's have a look at the algorithm. So that's the same graph of the end condition we were looking at earlier. And how does the algorithm work? Well, it scans through the basic blocks of a graph in a special topologic order. You find the details in the paper. It generates new outgoing edges as it visits each block. So we start from an empty edge set and we keep adding edges as we go. Now, when we process this first block here, which has a varying branch, we first observe that this block has two successors. It has successor B and D at index 1 and 3. And if we encounter a varying branch, what we're going to do is we're going to extract the minimum element of that set with regards to the block order, which is B1, and we're going to add only one edge from A to B. So the varying branch in A has been removed. There's only a single unconditional control flow edge now. However, we still have to account for D3. We can't just ignore it. We have to execute it if we executed A. So what we're going to do is we're going to add a deferral edge to all the new successors of A here from B to D, meaning that every path that reaches B in the new graph has to execute D eventually, and this is a post-dominance constraint. So this is basically a sketchpad relation that we keep maintaining during the algorithm. So this completes the processing of the first block A. Let's now continue with the next block B, which is a uniform branch. So in case of a uniform branch, we can have multiple outgoing edges, and we're going to find a new successor for each case of the branch. So let's have a look at the first case, which branches from B to D in the original graph. So to find a new successor, we're actually not only going to take the successor set we had in the original graph, but we're also going to add all the deferral targets that are tagged to B. And we do that for varying branch as well. This just wasn't necessary for A because the deferral relation was initially empty. And again, we're going to extract the minimum to find the new branch target. And all the remaining blocks we're going to add as deferral edges to D, but this set is empty, so no new deferral edges. If we now continue to the second successor for the false case of the B statement, B branch, we'll see that, okay, we join the successors, C, and whatever is deferred at B, namely D, and we compute the set. Now we extract the minimum, which is just C2, and D3 is deferred. So we're going to add the deferral edge from C to D. And we'll keep going through the graph until we have completed, basically have visited every block. So to sum it up, we visit each block once in this special topologic order. We generate new outgoing edges as we go through the graph. And finally, the deferral relation is empty, meaning there's no red dashed edges left, and the edge set is complete. And more importantly, no varying branches remain, but we are able to preserve some of the uniform branches. And that's the algorithm. So let's have a look at the properties we've proved for this. First off, we've proved correctness, namely that the traces and the partition that you will see the same traces in the original graph embedded in the partial linearized graph, and whatever is executed in the partial linearized graph is actually part of the original graph. We show preservation of uniform control dependence. I'm going to talk about that a bit later, but it basically means that we can use fast, unpredicated SIMD instructions if we can show that the predicate of a basic block is uniform. We also show a condition for the preservation of uniform branches, which we exploit to come up with reliable transformations for unstructured diversion control flow, as we'll show later. And the proofs are available in the ACM digital library as supplementary material, because it's 4 pages of proofs. Now let's have a look at the first property, uniform control dependence. If we're in a structured setting, like here, then the predicate is a conjunction of all controlling predicates of the statement. So in an AST-based language, a structured language, for example here, the statement S is dependent on all of these conditions, namely uni0, var, and uni1. It's a conjunction. And this is, since var is a varying condition, this will be the predicate of S. On the other hand, if all controlling conditions of a statement, as shown here for T, are uniform, like uni0, uni1, and uni2, the controlling predicate is again the conjunction. Since all of these conditions are all uniform, we will only execute T when this condition holds. So we can use unpredicated SIMD instructions for T, since we'll only ever reach it when everybody wants to execute it. And this is kind of obvious in the context of structure control flow and AST-based languages. So in quintessence, it's basically if you can use fast unpredicated SIMD instruction if the predicate is uniform. But this is absolutely non-obvious for unstructured control flow graphs. And in fact, if you ask a question, so what do current techniques deliver in the context of unstructured control? Well, there are no guarantees for this. This property doesn't actually hold, and nobody's even claiming it. But we've actually proved this for our approach. So we're the only approach that gives you this guarantee currently for unstructured control flow. And this is this preservation of uniform control dependence property. Let's talk about the second property that you can exploit, which is the preservation of uniform branches. So we show this for two techniques in the paper. The first technique is a transformation to transform divergent loops into uniform loops. Second is an approach to skip sections that are all false in the CFG. First part you find in the paper, second part we show here a little bit. So what is BOSC? This is basically branch on superword condition codes, which means if I have a branch in my code that's rarely taken, normally it would have to if convert it, so this will be often executed at runtime with a false mask. So what do? Well, you add a superword condition for this predicate, meaning that we will only enter the section here if this is true for any thread. So we can skip over it if this predicate vrare is actually all false at runtime. And this is pretty clear in the structured setting again. And you can get this with the coherent if, cifs keyword in ISPC, and there's a variant for CFGs as well that requires, however, an additional predicate hierarchy graph, so you need to maintain additional data structure. And we show an approach which is completely CFG based. So how does that work? Well, going back to the property we have, basically if A dominates B and A has a uniform branch, then we guarantee that this branch will be preserved. How do we exploit this for BOSC? Well, if we look at this code here, this is the control flow graph snippet that corresponds to it. We can simply add a uniform controlling condition, very much like in the AST in the control flow graph. And we guarantee this will do the right thing. So it will skip this section if vrare is not all true. It will skip, the section if vrare is all false. And this works without a predicate hierarchy graph or any additional data structure. It's only based on a local CFG transformation. And we can also nest these gadgets here to get the effect of having nested BOSC, which was also presented in earlier work. So we evaluate our approach on the region vectorizer, which we implemented. It's a vectorizer for scalar LVMIR that supports arbitrary divergent branches and reducible loops. And this implements partial linearization. And we evaluated our approach on AVX512, on AVX2, so on x86, and also on ARM machines with support for advanced SIMD, so 64-bit Neon. And so for the first part of evaluation, we looked at tree structures and traversal codes of tree structures adopted from the trilogy benchmark suite. And this is a KD tree, a bounce hard tree, vantage point in a binary tree. We actually added the binary tree to the suite. And we look at kernels that operate on these data structures, for example, like a one-nearest neighbor search, a k-means algorithm, point correlation, and in case of the binary tree, it would be an element search. And importantly, these were all implemented with scalar C++ code, only using these any all intrinsics. So we didn't need to modify the front end, unlike it is necessary, for example, for ISPC. And if we look at our results, you see we compare it to full if conversion, since this is the basic approach that's implemented in LVM and Clang. And so the baseline here is over Clang 03. So you just write this code, you run Clang 03, which includes an SLP vectorizer and LVM's automatic loop vectorizer already. And we get an average speed up of 2.11x in this suite. And we only see one slowdown below the baseline here for the point correlation, for one point correlation benchmark, since this was high dimensional data set, so we got a lot of control divergence in the traversal. And if we look at the utilization, so initially I showed that partial if conversion improves utilization of SIMD units. You see that compared to full if conversion, shown in blue here, we improve utilization, and the speedups correspond to improvements in the utilization. We conducted 2 case studies for each one for the transformations that we had. So one of the transformation, one is for BOSC, so the skip or false gadgets. And we looked at the Spec 2017 NABS benchmark, which contains 3 hot loops which dominate the runtime of the application. And we inserted 3 BOSC gadgets in the first and the third loop, which introduced unstructured control, so you needed partial linearization to handle it. And we compare against ICC, GCC, and again, Clang 03 with profiling information, actually. And as you can see, we outperform all 3 baseline compilers, and we also outperform our own vectorizer without the insertion of the gadget. The second case study was concerned with the divergent loop transformation. And in that benchmark, we looked at a key kernel of the Open MC Monte Carlo Nutanix application. And this is basically an irregular data structure traversal nested inside a vectorizable loop. So we vectorized the loop, and then we vectorized that traversal along with it. And as you can see, we're about twice as fast, again, compared to ICC, best of ICC, GCC, or Clang. To sum it up, I presented partial linearization, which is a fast and simple partial if conversion algorithm, which enables ISPC-like programming with control flow graphs. Partial linearization has provable and exploitable properties that you can use to optimize diversion control flow and implement reliable vectorizers. You find our vectorizer on GitHub at github/cdl-sauerland/rv. Thank you. I'm ready to take questions.
We have time for a couple of questions.
Hi, Shripati Pai from the University of Rochester. So you do know that GPUs handle divergence in hardware, which kind of simplifies the compiler part of it. So do you have any insights if this would benefit GPUs or CPUs with hardware branch divergence units?
Yes, it can, because in fact, if you're compiling, so that is in particular true for NVIDIA hardware, at least in the most recent generations, we have separate program counters per thread in a warp. So they can handle divergence entirely in hardware. But if you look at AMD hardware, for example, they need more support. And they also have transformations similar to this, actually. But again, they use a structured approach. And I think they might benefit from this or similar techniques.
OK, thank you.
Good talk, thank you. A couple of very quick questions. One is, it was not very clear just before the experimental data if you actually perform manual transformations also on some benchmarks. You seem to have converted to scalar C++ code some of the applications. I didn't get this.
Yeah, so, well, we implemented these traversals in C++ code. So it's scalar C++ code. And some of the kernels are written in a vector length agnostic style, like ISPC. But we did not have to use ISPC because we could use our vectorizer to
this perform. I got, but what's the reference then? So you had your own implementation of those benchmarks?
Yes, so it's also C++, and I think some of them were in Java, so there are various implementations actually.
Okay. So functionally, it does the same thing, but
yeah,
you have your own. Okay.
Exactly.
And my second question was more on the more related to data divergence. So some of these benchmarks may have irregular access patterns as well.
Right.
So what was the assumptions you made about the vectorizer's capability in those cases?
Okay, so we assume that you have a data parallel loop. So the loop iterations are parallel. So we may assume that there's no alias between iterations, if that is what you're referring to.
Okay. Yeah. So there's no specific analysis about these access patterns. Okay. Thanks.
So we work on the transformation part here.
Yeah. Hi, thank you. So I was just wondering how control flow unswitching actually relates to this work. So I mean, for the examples that you showed, I mean, if you do, so like you had a param there, and so if you generate 2 versions when you unswitch control flow, so how does it interact with whatever you are doing there? Does it?
Yeah, that's actually a good question. So if you apply such techniques, you can basically combine them with partial linearization. So you can use this for parts of the loops maybe, or you can do versioning, but in the end you still have divergent branches that you have to get rid of. And for that you can use partial linearization again.
Okay, I see. So if you do unswitching before, so does it? How does it affect the quality of the result that you get? Or
so if you do unswitching, it might improve the performance depending on the benchmark. But yes, there's some potential to, I mean.
Okay. Okay. Thank you.
Yeah.
All right. Let's thank Simon again.